Welcome to this presentation of a concrete example of process communication in the myHemera platform. We'll start by defining the notion of processing scheme and explaining its role. We'll then briefly present the main blocks of the platform's architecture, and we'll end up with a presentation of the various steps in the calibration of a Hull-and-White volatility surface. myHemera platform is a platform where any user can plug and play their own implementation of a quantitative model. So, for a given task to execute, the system has several executables that can apply for the job. Each user can therefore specify in his or her main context, or in the specific context of a report, what executables will be used to carry out the various tasks that are needed. You can see in the central text window a fraction of a processing scheme. For each model type here, zero coupon, caps and floors 1 factor, credit default swaps, FX, and to default credit baskets, in a script based on if, else, switch, and case syntax, using some input variable, that is, some characteristics of the zero coupon curve which are specified on the right part, here the label and the currency. The user will define the value of output variables also listed on the right. For the zero coupon stripper, the output model binary, which is the name of the executable to be used, and the output data source corresponding to the public or private source of the market parameters. The list of available executables is also given on the right part of the web page. Through these scripts, community users have the full flexibility to specify for each computation context the executable that should perform the task, and for each transaction they can specify what market parameter structure should be used. Let's now have a high-level, simplified description of the platform's architecture. The block highlighted in red corresponds to our web host, Amen. Here we have displayed 3 machines. The cloud-shaped area corresponds to the Amazon EC2, that's an acronym for Elastic Computing Cloud. myHemera uses the branch of EC2 that is located in Ireland. This is our main HTTP server. It's an Apache server with PHP add-in and several C and C++ Hemera finance concept dynamic linked libraries. These DLLs communicate with a series of routers. These are compiled processes that focus only on the dispatching of tasks and on identifying where the objects are stored and processed on the grid. The next component of the platform consists in compiled application servers located on the cloud machines and on Amen machines. Please note that what's represented here as a single process server is in fact made of several processes communicating via IPCs. We also use a main MySQL database server, and on each connected machine a local MySQL database server used to store security and identification elements. Let's come now to our concrete example. A user would like to visualize on his or her internet browser a calibrated Hull-and-White volatility surface with local volatilities. The query is sent from his local computer through internet to the HTTP server, that is, to the Amen machine. The Apache server calls a PHP function that is just an interface to a Hemera finance concept DLL function. The DLL function, loaded by the Apache server, opens a listening connection to the cap floors router and calls the router via TCP/IP sockets, which are comparable to telephone communications, to ask for the calibrated surface. The router checks if the object has already been attributed to a computation server. Since it is not the case here, it will attribute the object to an idle server or put it in a waiting queue if all servers are busy. Also, via a node.js HTTP server, the router will send back information about the server status so that the users can get real-time information on the grid activity. An idle server gets the job. The server asks the processing scheme for the name of the executable to do the job in the given context. The server launches the executable if needed and asks it to perform the stripping. The quantitative module asks back for the volatility surface definition and for the market values of its components, but also for a zero coupon curve. The server then asks the zero coupon curve router for the stripped zero coupon curve. The router checks if the zero coupon curve has already been attributed to a server. If not, it attributes the object to an idle server and sends it the job to be done. Just like the capflow router, it also feeds back real-time information on the grid activity via a node.js server. The server asks the processing scheme for the quantitative executable, that is, the output model binary, to be called, launches and calls the module. The zero coupon curve stripper calls back the Hemera server to get the curve definition. Then it strips the curve and sends back the stripped curve to the server in XML format. The server sends back the result to the router, and the router sends back the results to the capflow server. The capflow server launches the same zero coupon stripper executable as the one that stripped the curve. It gives it the stripped curve XML so that any interaction between the two quantitative modules can be done at high speed in shared memory, avoiding delays and network jamming. The hull and white module gets the proper zero coupons and volatility surface structure. It calibrates the volatility surface to match the market prices. It sends back the result in an XML format to the server. The server subscribes to notifications of the zero coupon curve used by the volatility surface from a modification notification server. The server then sends back the results to the router, and the server sends this back to the Apache server. The Apache server launches the same executable as the one that calibrated the volatility surface and gives it the XML calibrated surface so that any computation on the vol surface between the Apache server and the quantitative module can be done at high speed through shared memory segments. The PHP module gives the display info to the Apache server, and the information is displayed on the web browser of the client. Now highlighted is the Amen block. Then the zero coupon server block that can run anywhere on the web. Then the capfloor one-factor interest rate module server block that can also run anywhere on the web. Then finally the client's machine. This concrete example showed how, through separate sockets, with a sophisticated processing scheme and a plug-and-play architecture, one can have a naturally distributed solution where quantitative modules are always calibrated to the market parameter values with an optimization of the network load. Thank you for your attention.